All right, welcome everybody to this pre-recorded part of the SC 2020 BoF on the MPI forum. In the MPI forum in particular, we're getting very close to MPI 4.0. We have some exciting news there, and we also invite everybody to give us feedback on the current state of MPI 4.0. My name is Martin Schulz. I'm from Tech University of Munich, and I'm currently the chair of the MPI forum. I'll be presenting this in kind of a panel style together with several colleagues from the MPI forum, which I'll introduce slide by slide. We decided to make this kind of as a live cast from the MPI forum meeting that we had in late September, and so that's kind of the style we're going for. So you're going to hear an actual recording from the MPI forum in this pre-recorded part of the BoF. So let's get started with this. For those of you not familiar with the MPI forum drives the MPI standard, it's standardization body for MPI. We discuss all additions and all new directions for the standard in this standardization body. We're also responsible for looking at the correctness standards. So if there's any feedback on that, we take this from the community, also from our own internal quality management, and then we try to adjust the standard as needed. And of course, we present the MPI to the community through meetings like this. Typically, we would meet this in person at Supercomputing and ISC. This year, unfortunately, we have to do this virtual, but hopefully this will still be interesting to all of you. The forum itself consists of several officers, a chair, secretary, editor, and a convener, and most importantly, a series of member organizations who help us drive the MPI standard forward. Contrast to some other standardization organizations, we have an open membership model, so any organization is welcome to participate. By participating in one of our meetings, you become a member of the MPI forum, and then you can help us drive the standard forward. The forum itself consists of working groups where the actual real detailed work takes place, and then the actual MPI, all the changes to the actual standard then get discussed, changed, modified, and hopefully ultimately ratified. We have typically always had 4 physical meetings each year. With COVID-19, of course, that had to change, so we're actually meeting virtually at this point. We typically had 3 of these meetings in the US and 1 with Euro MPI, wherever Euro MPI happened to be in that particular year. We hope to get back to that modus, but right now we're meeting virtually. And so if you're interested in joining the forum, actually now is a good time because you don't have to travel to actually participate in the MPI forum. The working groups meet by phone. And I said that's where a lot of the preparation work is done, and then there's the plenary full form work where we then typically have had at these physical meetings, which we now do also virtual. I said everybody's a member of the MPI forum. You participate. The big thing is that when you become a voting member, and that just depends on attendance. If you attend often enough, if you're present at 2 of the last 3 meetings, including the current one, you're eligible to vote. So we want participation in the forum for you to help influence the standard. So if you're interested enough that you show up for enough meetings, you will also help. You also get allowed to vote for the standard. The working groups that do the bulk of the work, and I'm not going to go through all of those in detail, but we basically have working groups along major topics. You'll see the current list of the working groups and the chairs of this working group. If you're interested in one of these topics, feel free to approach the respective chairs, or feel free to approach me. And we'll make sure we'll put you in contact. And then so these working group meetings are mostly done by phone. So it's very low threshold to participate and help us drive the standard forward. The status of MPI, if you follow this, we have ratified MPI 3.0 in 2012. So it has been a while, but with some major new additions. We had a minor update in 2015, and all of these changes have been ratified. Use the functionality of MPI 3.0 and 3.1 in most MPIs. And then we have started after that working on 4.0. There was a larger changes there. This was, it took us some time again, but this is coming to an end. We have a release candidate, which we are publishing with the Supercomputing Conference this year. And this release candidate is also available on the MPI forum webpage for you to download, and we welcome, of course, feedback on this one. We hope to ratify the actual document in the coming months. So now is a really good time to give us feedback and let us know if you see any particular problems with it, or if you see something that still needs fixing. So please speak up and give us feedback. There are several major new additions to that. Here's a first list to that. We'll go through each of these additions one by one. and we'll have the respective working group chair or one of the main active proposers of this particular edition. First overview, talking about something called big counts, persistent collectives, partition communication, some solutions for hardware topologies, new concept called MPI sessions, better fault handling, and a new tools interface is some of the really big additions to MPI 4.0. So you see there's quite a bit of new coming in MPI 4.0, so this is really a big step. We're really looking forward bringing this to the community. And so with that, I would like to invite the individual participants in the MPI forum who have agreed to participate in this pre-recorded material to say a few words about the respective editions. First, we're going to talk about big count, and I would like to invite Jeff Squires from Cisco to talk about this.
Hello, everybody. As Martin said, my name is Jeff Squires. I'm from Cisco. I'm going to talk to you about big count, which we inside the forum lovingly called the embiggenment. The whole point was that in the current interface, many of the counts of parameters that are sent into MPI are of type int, which is almost always 32 bits. And this creates some real constraints for real world applications. And so effectively, although there were workarounds, effectively it made it a bit more difficult to actually send very large volumes of messages around, or very large messages around. There are a couple of cases where the trick of using data types also didn't work. They're very esoteric corner cases, but they did arise in actual real world MPI implementations. We did use, we did talk through a number of different possibilities of how to make this better. So could we just change int to MPI count? And that's an opaque type, and then an MPI implementation could just change what the type of MPI count was under the cover, say something to 64 bits. This led to all kinds of backwards compatibility issues, and that was also a real world issue for a lot of both MPI implementations and consumers and customers and users out there. So that was rejected. We also looked at polymorphic bindings for C, notably using C11. There were a bunch of corner cases and things that ended up not working out there as well. A lot of very detailed things that aren't worth going through here. We also looked at the duplication of interfaces. So using one binding with an int and one binding with an MPI count. So suffixing MPI send with MPI send C, for example. This turned out basically to be the least bad of the solutions. So in C, that is what we're going to end up with. You'll have MPI send and MPI send C and so on. In Fortran, it's much more transparent because Fortran does have polymorphism native to the language. So there was a lot of general type rules updated for the bindings and a lot of verification. We spent a ton of time verifying all these bindings, which led to a lot of errata tickets, a lot of thought, a lot of research, a lot of verification behind the scenes in both the working group and with the help of all the chapter committees and the working groups inside the forum itself. So the end result is that you'll see a lot of new routines that have C_C in them. And if you're a Fortran programmer, the result is much more transparent.
Great, thanks, Jeff. The next topic we want to talk about is persistent collectives. So I'd like to invite Tony Scalium from University of Tennessee, Chattanooga, to talk about this.
Thank you, Martin. I'd like to talk about the persistent collective operation we've added to MPI 4. They cross-cut both the collective communication chapter and the topology chapter that we had in MPI 3.1 and earlier, and they focus on the idea of essentially planned transfer. We had this idea of persistent point-to-point communication all the way back to MPI 1, an idea in that particular case where you could have a send in it or receive in it, set it up once, use it multiple times. And that was a genesis for persistent collective operations, which are all about set up once and then reuse, with the idea that those could be optimized a lot better than MPI 3.1 collectives that are either blocking or non-blocking, because the implementation is told in advance what's going to happen and then the arguments are frozen. So we know that there are a lot of programs that will set up a collective and use it with exactly the same arguments. They'll specify something without changes except for the buffer contents. They'll do it over and over again, and that allows the implementation to lock down resources, figure out what its plan of execution is going to be, particularly maybe pick among a complex set of algorithms heuristically, and therefore give the right kinds of performance to an application that's willing to live with the restrictions of setup, and then have fixed requirements, except of course for buffer contents that have to change for the communication to be useful. So we learned a lot from prior work in this area with sends and receive, inits, put in, collective operations, and now implementations are beginning to see what we've seen both in research and in practical implementations, people beginning to take advantage of these operations to get more performance. The final feature is that these operations also are allowed to start in different orders across the groups of processes. So they're a little bit more general in their ordering with regard to other collective operations, and we'll speak more about that in MPI4. So look for this as a way to get higher performance collective communication in MPI4 and beyond as implementations add optimization to our existing functionally working implementations that are already appearing in open source implementations.
Great, thanks, Tony. So next, we're going to talk about partition communication. I would like to ask Ryan Grant from Sandia National Labs to talk about that.
Thanks, Martin. So partition communication is a new chapter added in MPI 4.0, and it brings in some new core ideas there. But the high-level takeaway is that it's meant for highly efficient, highly concurrent communication. So the partition communication that's in MPI 4.0 is built on the concept of persistent operations, where we take a single send operation and split it into partitions. The idea here is that for very highly threaded or highly concurrent codes, you can do a single MPI operation, but express data movement on a much more fine-grained mechanism. So the idea here is that as you fill partitions in a buffer that's meant for communication, you can mark these things as ready using an MPI p-ready call that's lightweight and meant for threads, or even lightweight threads like GPU threads or accelerator threads to do these things. Likewise, receive buffers can also be split into partitions, and it is possible to receive individual notifications on each arriving partition that happens as well. And what this essentially enables us to do is have partial data transfers. So one of the takeaways that you can think of this for is being able to actually make MPI calls, specifically the MPI partition communication MPI p-ready calls, inside of things like parallel OpenMP loops and potentially GPU kernels efficiently, and be sure that those are going to operate efficiently for you. And the notifications on both the send and receive side are lightweight. So when you send something, you notify MPI that you're going to send that piece of data. MPI, that notification is fairly light. So the idea here is that it can be driven from accelerators or individual threads and still give us good performance. Now, you may need to have some additional optimizations and synchronizations, and this is something that we're working on for MPI 4.0, some GPU optimizations to make kernels able to trigger operations that are set up on the CPU side. So the CPU sets up the communication operation, and inside your GPU kernel, you can actually trigger these messages to move to the other side. I should say partitions there rather than messages. So if you're interested in how to apply MPI in highly concurrent situations, bringing MPI into your existing OpenMP loops inside your applications, or using MPI in GPU optimizations, please go take a look at the new partition communication chapter and pay attention to what's going on in MPI 4.1, particularly if you're interested in GPUs, as we're introducing more functionality to further optimize things for those platforms. Thanks, Martin. Back to you.
Great. Thanks, Ryan. Right, and another thing we addressed in MPI 4.0 is the rising complexity of hardware topologies, and I would like to pass to Guillaume Mercier from INRIA to talk about the new features.
Thank you, Martin. So I'm Guillaume Mercier from INRIA Bordeaux Institute of Technology, and I'm currently the chair of the Hardware Topologies Working Group in the MPI Forum. And in this particular working group, we've been discussing new ways to better exploit hardware details at the MPI application level. Indeed, MPI is hardware agnostic, but that doesn't mean that hardware details can be leveraged by application users. So the current situation is that hardware becomes more and more complex. First, the current trend is to increase the core count. And then, second, memory hierarchies become more and more intricate with deeper levels of memory resources. Better communication performance can be expected from processes that do actually share hardware resources, for instance, a NUMA node or a cache level. Also, the mapping of processes to resources is critical for performance as well. We need means to let the user exploit this process locality, and the notion of communicator is relevant in this context. So we added a way to create such hardware topology-aware communicators. We decided to expand an already existing communicator creation function, which is ComSplit type, and to introduce two new split type values for it that correspond to so-called guided and unguided modes of splitting the input communicator. With the guided mode, the user provides an info key that specifies the hardware level at which the splitting is done, for instance, NUMA node, package, L3 cache, etc. With the unguided mode, the input communicator, MPI ComWorld most of the time, but not necessarily, is split into subcommunicators that correspond to the next hardware resource available in the hardware hierarchy. For instance, if a user splits a communicator that corresponds to a package that features CPUs, subcommunicators corresponding to each of these CPUs will be produced with this unguided mode. The user can proceed iteratively on each produced subcommunicator to create a hierarchy of communicators that corresponds to the hardware one. Last, we don't have a function to query the available info keys in the guided mode yet, but we plan to introduce it in the future, and we also plan to introduce new features for hardware topologies in the next version of the MPI standard. Thank you very much.
Great, thank you very much, Guillaume. Another big topic which you may have heard about is the MPI sessions concept, which changes the way you handle MPI initialization. I'd like to ask Dan Holmes from EPCC to talk about that.
Thanks. So yeah, hi. MPI sessions is a new concept in MPI. It's basically, you can view it as a way of breaking up what MPI init does, or MPI init thread, into 4 steps four procedures that you would call instead. So you don't have to call MPI init anymore. Now you can call MPI session init and then proceed through this set of procedures so that you get to a communicator, but without calling MPI init. So that's one way of looking at it. There are also other uses of it. In particular, it allows some level of isolation between what happens in one session and what happens in another session. And so this is really good potentially for libraries that are built that use MPI. So the general idea, the basic scheme of how to do this is that you would call MPI session init instead of MPI init. That is a local call that doesn't do very much. It just gives you a session handle. That handle then allows you to query via MPI what sets of processes there are. It gives you some information about the resources that are available on the machine. And then you can select from those sets of processes, named sets, and pick one or more of them and create MPI groups from those set names. And that is an ordinary MPI group, something that you'd be used to working with already. From that, you can then create a communicator, and that then operates exactly like any other communicator that you're used to using at the moment. So if you wish to create something like a ComWorld, you could do that by using the process set, which is the MPI world set. That would be the same group of processes, and it would create a communicator that was very similar to ComWorld, but it also allows you to do something less than that. You could create a smaller communicator than that, while still having access to those resources if you wanted to create something bigger or something else at some later time. So this allows reinitialization of MPI. It allows multiple concurrent initializations of MPI. So the main application can initialize MPI in its own session, and each of the libraries that that application uses could also initialize their own session, and they can all then interact with the resources that they have available and not interfere with each other because they're isolated from each other. So this is seen as a first step towards bringing some of the information from the resource manager into MPI, making it available in MPI. We have ideas already for how to do this, how to do more than this in the next version of MPI, but obviously that's still early stages right now. So that's all from me.
Great, thank you very much, Dan. Fault tolerance was a big topic that we had for years, but we don't have a final solution for that in the MPI standard. There was a lot of improvements made in this area, and I'd like to ask Wesley Bland from Intel to talk about that.
Hi, so as Martin said, we have been working on fault tolerance in the MPI forum for quite some time, and obviously we are not done with everything we intend to get into the standard at some point. We did get a lot of things into MPI 4.0 that help with what you might refer to as sockets-like error handling, and this can help a large class of applications that want to be able to have some basic resilience from MPI. So our goal here, rather than providing a full recovery solution, is to better specify the error handling that an application can do and what a library, an MPI library, should provide. So to start with, this means better defining the state of the library. So for instance, if a MPI call returns success, it doesn't necessarily indicate that everything is successful everywhere, just that the function that was called returned in the way that the user can expect based on the way that function is defined. We also made it more clear that errors should be localized to the operations or to the processes that call them. So for instance, if a process is allocating memory with a function like MPI alloc mem, that error should be raised on com self rather than com world. It shouldn't cause all other processes to fail if there were an error in MPI alloc mem. Another example of trying to localize errors comes from just specifying that the predefined error handler, MPI errors are fatal, should be the only one that causes the entire job to abort, as opposed to something like MPI errors return, where the function should return with an error code rather than aborting the entire job. We also added a new error handler, which makes it more clear when certain processes in the job should abort if there is a problem. This is MPI errors abort. So errors will cause only a subset of processes to abort. And then we provided a way for applications to specify the default error handler at MPI exec time rather than needing to change the application itself. So if you want to run your application with error handling on in one instance, you can, and off in another instance without having to change the source code. So based on this, you can have some rather simple sockets-like error handling without a lot of extra work. This enables manager worker type of applications and many other more non-traditional applications for what people might think of as an MPI app. But this does enable new applications that maybe don't use MPI today that we see from the enterprise. And moving forward, we'll continue with the more large-scale fault tolerance that we've been working on for a while. And that's all on error handling this time around. Great,
thanks very much, Wesley. And then last but not least, there was a lot of work also on the tool side of MPI. And I would like to ask Marc-André Hermans from RWTH Aachen to talk.
Yeah, thank you, Martin. My name is Marc-André Hermans. I'm from RWTH Aachen University, and I'm the current chair of the Tools Working Group. And for MPI 4.0, we introduced MPIT events, which is a callback-driven event information interface. And the key idea is that it complements the existing interfaces of PMPI, which helps us to intercept MPI calls, but keeps the MPI implementation more as a black box, and MPIT, the tool information interface, which gives us a glimpse into the MPI library, but only shows us aggregated information. For the design of MPIT events, we wanted to be as close as possible to the existing MPIT semantics. So we don't mandate any specific event types and state transitions to be provided by a library. Because there are no standardized event types mandated, the event structure can be inferred at runtime from the tool. As I said, the interface is registered, is callback based, so the tool can register callback functions to be called by the runtime. One of the key ideas here is that the runtime may defer callback invocation to a more convenient time, and the tool can then query the event time in the past or of the past when the state transition actually happened. That may be helpful to reduce restrictions on the callback functions, which is also inferable on the callback invocation. And finally, also the callback information can be either queried item by item or en bloc. Back to you, Martin.
Excellent. Thank you, Marc-André. So you heard about all the big additions we did for MPI 4.0. Of course, there's plenty of other small additions as well that we don't have time to go through in all detail. But we added some assertions that can help you interact with the MPI library to guide optimizations. We can basically assert certain traffic patterns that you do or don't do. With that, the MPI library can optimize. We made just to info key propagation and community duplication, which may be interesting for some of you. There were some clarification that was made if what it means to query the info object. If you're relying on that property, I would encourage you to take a look in that particular chapter. We deprecated send cancel, which many of us felt was long overdue because it caused a lot of problems. We did some small fixes in the tools information interface. And then also, because of all the changes in tools and sessions, the info object is now available before in MPI initialization. Fault tolerance was another case where we needed that for. So also these small changes have happening over the time. So you see a lot of changes happen. MPI 4.0 will really be a major new release, which has a lot of new functionality in it. So what's the next the steps for that? So as I said, the release calendar is available. Please take a look at that. It's on the MPI Forum website. And we do want feedback from the wider community. If you see anything where you say that cause a problem or there's a mistake in there, please let us know now. Because the next steps after that is we're going to do a first validation and then the first vote towards the MPI 4.0 standard at the next MPI Forum meeting, which will be in December. And if everything goes well and we don't find any major mistakes, we do the ratification in February. But the idea is that what we have now in the release candidate is very, very close to what will afterwards will pass. So now is a good chance to give us feedback, to let us know if you see any problems with that for your particular application, for your particular system. If you haven't been participating in discussion so far, please use that opportunity and let us know. And the other good news is we talked to the major open source implementations, OpenMPI, MPitch, and MVAPitch, and all of them are already on track to implement these features. A lot of stuff has been implemented already or is planned for implementation, or they're actively working on that. I won't read all these things. These slides are available for you to take a look at. And of course, also the other versions that have been parts of, in some cases derived from those will automatically get this too. So MPI 4 will be something that's available relatively soon after we pass it for the wider community to use, which I think is very exciting as well. So I hope this gave you an overview of what we are doing in the MPI Forum, where we are with MPI 4.0, and how we're going to proceed to the next couple steps. And now, hopefully, we all meet each other again in the interactive Q&A part of the MPI Forum BoF. So hopefully see you there in a couple minutes. Thank you very much.